Hello everyone, welcome to our talk. I'm Chengyu Zhang.
I am Dominik.
Today we will together introduce our simple but unusually effective approach called type-aware operator mutation for testing SMT solvers. This work was performed with Zhendong. We first give a brief introduction to SMT problem. Given a first-order logic formula phi, for example, x greater than 0 conjuncts with x less than 0. The SMT problem is to answer whether we could find an assignment for the variables in the formula that makes the formula become true. If we find such an assignment, the formula is satisfiable. For this formula phi, since we cannot find an assignment for x that makes phi become true, phi is unsatisfiable. If we change the last 0 to 1, the new formula is satisfiable. Since x equals to 0.5 is a satisfying assignment. SMT Solver is a tool for solving the SMT problem automatically. Given a formula phi, an SMT solver will report the satisfiability of the formula. Many programming language-related technologies depend on SMT solvers. For example, symbolic execution, solver-edit programming, program verification, static analysis, program synthesis, and so on. In practice, SMT formulas are usually represented by SMT-LIB language. For this example, the first line is the declaration of variable x. The second line is the assertion for describing the formula. The third line is calling solver to give the satisfiability to this formula. However, like most software, SMT solvers could have bugs as well. For example, for this formula written in SMT-LIB language, SMT solver CVC4 correctly reports unset, while Z3 incorrectly reports set. It was a real bug in SMT solver Z3 that makes Z3 reports incorrect satisfiability. This is the most critical kind of bug in SMT solver, which is called Soundness Bug. However, finding bugs in SMT solvers is challenging. The previous work only found less than 30 confirmed soundness bugs in SMT Solver Z3, and a few or no confirmed soundness bug in SMT Solver CVC4, which indicates the difficulty of finding bugs in SMT solvers. To address this challenge, in this work, we proposed type-aware operator mutation, which found many more bugs in two state-of-the-art SMT Solver Z3 and CVC4. Then, we introduced type-aware operator mutation, this simple but effective approach for finding bugs in SMT solvers. Given a seed formula, on which both CVC4 and Z3 correctly report set, the purpose of the type-aware operator mutation is to generate new well-typed formula by randomly mutating the operators in the seed formula. For example, we randomly select the operator distinct from the seed formula. To generate well-typed formulas, it should be substituted with a new operator with the same type. The type of the distinct operator is receiving two int expressions and return a Boolean value. Then we list a bunch of operators that have a compatible type, and randomly pick one to substitute the operator distinct. Now we have our type-aware operator mutant. We further use this mutant to validate SMT solvers by cross-checking the results of two SMT solvers. For this mutant, CVC4 correctly reports unset, while Z3 incorrectly reports set. Then, we find a Z3 soundness bug via type-aware operator mutation. We could also chain type-aware operator mutations. For example, given a seed formula, we first select one operator and generate a type-aware operator mutant. Based on this mutant, we could further randomly select another operator to generate next generation of type-aware operator mutant. This process could iterate arbitrary times. SMT solvers will be validated by cross-checking the results using the mutants on the chain. For example, by using this second-generation mutant. For cross-checking the result of CVC4 and Z3, we found a Soundness bug. Then we let Dominik introduce our empirical evaluation on hunting bugs in SMT solvers. Dominik.
Thank you, Chengyu. I will now present the empirical evaluation. To evaluate type-aware operator mutation, we realized a fuzzer called OOPSLA, with which we conducted a bug hunting campaign from September 2019 to October 2020. We tested the two state-of-the-art SMT solvers Z3 and CVC4 in various configurations. For the test seats, we used the SMT-LIB benchmarks comprising over 300,000 formulas across many SMT logics. We have pre-processed these formulas to ensure that Z3 and CVC4 do not trigger any bugs on these seats. To date, our bug-finding campaign with OOPSLA found more than 1,000 latent unique bugs, which we reported to the respective bug trackers of Z3 and CVC4. Out of these bugs, over 800 were confirmed, and over 700 are already fixed by the developers. Among the confirmed bugs, 184 bugs are soundness bugs. A soundness bug occurs when the solver gives a wrong answer, for example a solver returning unset for a satisfiable formula or set for an unsatisfiable formula. The soundness bugs are the most critical bugs in SMT solvers. 102 bugs are invalid model bugs. An invalid model bug occurs if a solver returns a model for a satisfiable formula that does not actually satisfy constraints of that formula. As byproducts of our fuzzing campaign, OOPSLA found a lot of crash bugs. We also tested the SMT solvers under various option configurations. Note, however, that the majority of the bugs we found are in the solver default modes, which means without any additionally supplied options. And in fact, only a few bugs we found required more than 3 options to be triggered.
This table shows a comparison of OOPSLA with other SMT solver testing approaches. The bug counts shown here are based on confirmed bugs found in the default modes of the solvers and exclude bugs with options. Compared to previous work, OOPSLA found much more bugs in both Z3 and CVC4 totally, and also much more soundness bugs. This demonstrates the unusual effectiveness of OOPSLA for bug finding as SMT solvers.
Let us have a look at some bug samples. The following formula triggered a soundness bug in Z3's bit vector logic. CVC4 reports set on this formula, while Z3 incorrectly reports unset on it. In fact, the formula is satisfiable as the ternary BF(x)NOR expression is just a shorthand for the nested binary BF(x)NOR expression, and the equality should hence simplify to true. The root cause for this bug is an unsound rewrite rule in the BF(x)NOR operator. According to this rewrite rule, NRE BF(x)NOR operators are reduced to negated BF(x)OR operators. And to see why this is unsound, consider an example where all 3 variables ABC are equal to true. We first convert the ternary expressions into binary expressions, then evaluate the innermost of these expressions on both sides, and obtain true on the left-hand side and false on the right-hand side. The rewrite is only incorrect for the NRE case. For the binary BF(x)NOR operator it is admissible. Hence, Z3 gives unset on this formula. Here's another Z3 soundness bug on a formula with uninterpreted functions. Again, the bug is caused by an unsound rewrite. In this case, the last term of the distinct expression was missed because of a logic bug in a loop condition. The bug relaxes the constraint of the formula and causes Z3 to incorrectly give set. Here's the CVC4 soundness bug in string logic. For this formula, according to the SMT-LIB standard, the string index of operator returns the first occurrence of y in x at or after position 1. If y is empty, the result is the third argument, 1 in our case. Hence, the index of the expression could be less or equal to the string length of x. CVC4 exploits this in its string solvers, but misses the equality case. One of the CVC4 developers fixed this bug and thanked us for our bug report. Here's another CVC4 soundness bug in a formula with uninterpreted functions. Is caused by an unsought variable reuse in formula simplification, which makes CVC4 incorrectly report unset. This bug got a major label on the CVC4 issue tracker, which underlines its significance. This is a soundness bug in CVC4's symbolic square root implementation. The formula is clearly satisfiable for some negative square root x. However, CVC4 applied the following simplification. CVC4 reduces the square root of x to a choice of a real variable y to be the product of the square of x. The issue here is that for a negative y, no such x exists. And this although the SMT-LIB standard allows negative square roots. From our 1-year-long bug finding campaign, we have summarized some lessons which we would like to discuss here. First, we realized that the bugs found by OOPSLA are of high quality. We investigated the bug fixing commits for each of the bugs and found that the largest bug fix in Z3 changed about 500 lines of code, and the largest bug fix in CVC4 changed around 1000 lines of code. Most importantly, our bug reports inspired the developers overhauling some components of the solvers. Second, we have gained an understanding on the relative weakness of the components in Z3 and CVC4. We ranked the most influenced files with respect to bug fixes in Z3 and CVC4. This ranking shows that decision procedures for nonlinear arithmetic are among the weakest components in SMT solvers. Besides nonlinear arithmetic, rewriters are a weak component as well. Some related examples have been shown earlier. Third, we experienced that bug reduction can be challenging. As we have observed, 90% of all bugs found by OOPSLA are triggered by formulas of less than 600 bytes, and small-sized formulas save the bug fixing efforts significantly. We use CReduce, a C-code reduction tool, to help reduce SMT formula bug triggers. While CReduce worked well in practice, it is still not able to handle some specific formulas, like the formulas in bit vector logics. Hence, a nice and tailored SMT formula reducer would have been needed to assist our bug finding process. To sum up, SMT solvers are foundational tools for many PL technologies. To effectively test SMT solvers, we propose type-aware operator mutation, whose key idea it is to mutate operators of conforming types within SMT-LIB formulas. In our empirical evaluation, type-aware operator mutation found more than 1000 bugs in the two state-of-the-art SMT solvers, Z3 and CVC4. In fact, type-aware operator mutation can find many interesting bugs and has helped the developers robustify the solvers. Please check out our website for detailed statistics and bug reports. Also check out our Twitter account where we regularly post interesting bugs. Last but not least, we want to announce that we have recently released our umbrella tool Yin-Yang on GitHub, which also integrates OOPSLA and our SMT solver bug hunting approach Semantic Fusion, which we presented at this year's PLDI.